So in this video, we're going to talk about what are called voltaic cells or galvanic cells. All right. This is more commonly referred to as just simply a battery. All right. This is probably one of the most important applications of redox reactions. So what's the connection between redox reactions and a voltaic cell? All right. Well, we know that batteries are used for creating electricity, right? And electricity, if we would want to just oversimplify it, could be defined as the flow of electrons through a wire. All right. Well, we know that redox reactions involve the transfer of electrons from one atom to the other. All right. So it doesn't. It's not immediately understandable how you turn this process into a flow of electrons through a wire, but that's what we're going to talk about in this video. All right. So what do we want to start off with? We're going to start off with this redox reaction right here. And we mentioned this before. It's actually one of the examples that we gave in the previous video. And we mentioned that it happens in this direction. All right. And the reason that it happens in this direction is if you look at the activity series, we find both zinc and copper, you can see that zinc is higher. And what that means is that zinc would prefer to get oxidized much more than copper would prefer to get oxidized. All right. So if you put these together, if we allow copper ions to get reduced in the presence of zinc metal, all right, that reaction should occur. All right. And that's exactly what this reaction right here shows. All right. So what I'm going to do is, instead of going through the galvanic cell, there's actually an excellent video on YouTube that goes through this. But what I want you to remember while watching this is this basic concept that this reaction shows, is that zinc metal wants to give its electrons to copper ion. All right. When that happens, your zinc is going to become zinc plus 2, and your copper is going to want to become copper metal. All right. So the YouTube video, I've given the URL right here. It's actually by Tyler DeWitt. I'm not sure if you're familiar with any of his videos. I think they're pretty good. It looks like this right here, and I've actually linked it on my Canvas page as well. So take a look at this video, pay attention to it, and when you're done watching it, we'll kind of sum up a couple of the details that were in it. Okay. So this diagram right here sums up a lot of the major concepts that were in the video. All right, and a couple things I want to stress. All right, first of all, the terms anode and cathode. All right, the anode is the site of oxidation. All right, since oxidation is the loss of electrons, it essentially corresponds to the place in the galvanic cell where electrons are being pumped into the wire. All right, so remember, zinc wants to get oxidized. All right, if we take a look at this reaction right here, zinc wants to get oxidized. It wants to give its electrons to copper plus 2, which is this guy right here. And the thing is, in the cell, they're not directly connected. The copper ions are way over here. But that's what the wire does. It provides a path for the electrons. Once zinc loses its electrons, those electrons can flow through the wire and eventually combine with the copper ions that are in solution right here to become copper metal that gets created on the surface here, right? So the cathode is the side of the reduction. All right, the reduction is actually occurring in this side right here, so that's considered the cathode. All right, so there's also this term half cell. All right, so in general, a half cell is a metal that's surrounded by a solution that contains ions of that metal. All right, so this right here is a half cell because it contains zinc metal right here, but it's got a solution of zinc sulfate. All right, and so that's what makes it a half cell. It's a metal inside of a solution that's got ions of that metal. Right, this is also a half cell because it's got copper ions from the copper sulfate in the solution, but it also has a bit of the copper metal. All right, so there are names for the half cells. There's the oxidation half cell, which is the half cell where the oxidation occurs. This is the half cell where the metal is losing electrons. the electrons go through the wire, but then when they lose the electrons, it creates a positively charged metal ion. Those simply float out into the solution. All right. The reduction half cell is, aka the cathode, is where the reduction occurs. All right. So the source of the electrons for the reduction come from the wire. They actually would flow through the copper metal. By the way, most wires that you're going to find are made of copper anyways. All right. So it's flowing through copper here. It hits the copper here. It just keeps on flowing until those electrons hit the solution. And when they hit the solution, some of those electrons can combine with the copper +2 ions, and that makes neutral copper atoms that get deposited on the outside of the surface. All right. So last thing to stress is this thing called a salt bridge. All right, and that's just it's a tube that contains ions. All right, and the purpose of that is to allow it so that you don't get an overall charge that gets formed in one of the half cells. All right, so remember what's happening at the anode. All right, you've got electrons going this way, but you've got zinc +2 ions that are getting created and floating out into solution. All right, so this solution would be getting more and more positive as time goes on. All right. In contrast, on this side, we've got copper +2 ions that are leaving the solution, and we've got electrons coming into the solution over here. Sorry, into the half cell over here. So if copper +2 ions are leaving the solution to become neutral ions, this solution would be becoming more and more relatively negative. All right. Remember, there are the negative counter ions from whatever the salt. If we had added copper sulfate as your source of copper ions, all right, you would have the sulfate ions continuing to be in the solution here. And if the copper +2 is leaving, that leaves all those sulfate ions here. So it's becoming more and more negative, not because you're adding more negative ions, but because you're losing some of those positively charged ions that were in the solution. All right. So what the salt bridge does is it allows positive ions to flow towards the half cell that is losing positive ions, and it allows negative ions to flow towards the half cell that is gaining positive ions. All right. So that helps to maintain an overall neutral charge in both of the half cells. All right. So one last thing, whenever talking about voltaic cells, there's a shorthand way to draw this. All right. So even though copper, this particular reaction right here involving copper and zinc, is the most famous of all of the voltaic cell oxidation and reduction reactions, we could do this with any oxidation reduction reaction. All right. So theoretically, well, I should say any, but theoretically, you could find any combination of a metal and that's above another metal on this activity series, and we could make a half cell with one of the metals and a half cell with another one of the metals and create a battery. All right. So so a way to draw what you're doing in a battery is to use this little shorthand notation. All right. And here's the way it would work. What we're going to show here on the far left, and by the way, I should put solid here instead of copper 0. If you think about it, copper 0 would be neutral copper metal, and so that would be solid. So the thing on the far left is going to be the oxidation half cell reactant. You put a little slash next to that. You're going to have the oxidation half cell product. All right. You have the two lines right here that represents the salt bridge, and then this is going to be the reduction half cell reactant. All right. So this is the reduction half cell. Copper +2 is the reactant there, and then copper metal, or you put the slash, and then the thing on the right is going to be whatever the reduction half cell product is. All right. So any voltaic cell could be denoted by this shorthand notation. Right. Notice it doesn't just have have to be zinc and copper. All right. Note one thing, that if this is a voltaic cell, we would never have these on the left side because the reaction is only going to happen in that particular direction. So hope that helps, and I will be giving you some practice in drawing these shorthand notations.